What's up, guys? Welcome back to part 2 of this episode on fine-tuning BERT for sentence classification. I really enjoyed chatting with you guys down in the comments. So for those of you that have left feedback and asked questions, thank you. It's really valuable for me to hear what you guys are most interested in. And I'm excited to kind of dig into some of that stuff. There are some good questions. So please keep doing that. I love hearing from you guys and chatting with you. So in the last video, we prepared the Colab data set to feed it into BERT. BERT has these kind of detailed formatting requirements. So we looked at how to get our text ready for BERT. Now we're going to actually do the fine tuning. We're going to train our model on the task. And the Hugging Face library provides some help for us in this. They've defined a number of classes which can be used for various fine-tuning tasks. And the one we're going to be looking at is BERT for sequence classification. So that's what you use if you want to do text classification with BERT. I've linked to the documentation, the API docs, so those are there for reference. And let's get to it. So we'll import the BERT for sequence classification class. And this class has a function called from pre-trained. And what this is going to do is it's going to define in PyTorch the architecture for our model. It's going to build the 12 BERT layers and then add a single classification layer on top for us. And as part of that, it's going to load all of those pre-trained weights for us from the BERT layers. We're going to use the BERT base uncased model. So there's a small number of these models that you can choose from. Base is the 12-layer BERT model. There's also large. Large is something like 20 or 24 layers. I think the large model was really just for getting like a little bit higher results on the benchmarks. And I think the base model is probably the better balance of size and accuracy. And then, as far as whether to use cased or uncased, I have no idea. I think the example that this is based on used uncased, so that's what we're going with here. This is an important feature here. Since we're doing classification, here we're doing binary classification. We're classifying the sentences as either grammatical or not grammatical. So we have two categories, two labels. If you had a multi-class classification problem, then you can put whatever number of labels in here that you want. So this does support more than just binary classification. Then there's a couple additional configuration options here. One is that you can have the class output all of the hidden states from the model. So that's useful if you want to do something like create sentence embeddings maybe from some of the hidden states. Or even just maybe explore what's in there. There's also the ability to output the attention weights, and honestly I don't know what that's about exactly. I'll try to figure that out and address it in another video, but that's there as well in case you're familiar with it. So we'll run this cell and it's got to actually download the weights for us. So if you remember, there's 109 million parameters in the 12 layers of the BERT model, and it takes over 400 megabytes to store those. So all the weights for those 12 BERT layers are pre-trained. They have there's intelligence there, but then the weights for the classification layer on the output are randomly initialized. So those are meaningless right now. We need to train the model in order to make those weights logical. The next step is to call model.CUDA. That puts the model on the GPU. And I believe that call will also print out the definition of all the layers of this network. I find this this output kind of difficult to read through, especially not completely understanding how all of these pieces work yet. Something I did find a little more interesting, though, is that you can extract all of the parameters from the model. You can call this named parameters function, and that returns a dictionary of parameter names and then the parameter values. And I'm just turning that into a list here. And this cell is going to output some of the parameter names and then their dimensions. So for each parameter in this parameters list. The first 5 are for the embedding layer. So we'll output the parameter name and then the size of the parameter. And then we'll do that for the first transformer layer. Remember there's 12 transformers, and then the output layer. So there's a total of 201 different named parameters in the model. The embedding layer is where we start. So if you look at the word embeddings there, there's the vocabulary of about 30,000 words. We learn here that the size of these embeddings are 768. And then the maximum sentence length is 512 tokens. And BERT has an embedding for each of those 512 positions. Yeah, and then on the transformer layer, you can start to see some of what's here. There's self-attention, there's these query key value weights, then there's output attention. So we'll have to explore those more later on here. And then finally, we've got the output layer. So we've got a pooler here, and then our classifier. And if you look at our classifier, we just have two outputs and 768 weights each. So we've got, like 1,500 weights on the output layer that's doing our classification, and then 110 million behind that on all these BERT layers. So, I mean, that gives you kind of an idea of like, how much knowledge is already in this model that we're leveraging. Okay. So as we go into more of this training code, it's going to become more and more, PyTorch dependent. But I'll do my best to kind of explain what's going on here. So there's 2 objects that we need to create before we can get into our actual training loop. And those are the optimizer and the learning rate scheduler. So the optimizer is the object that actually performs the updates to our weights. So we'll call optimizer.step down in our training loop, and that will actually change the parameter values based on the update rule defined by Atom. And we have to define some things here. We have to choose an initial learning rate. I think these are author recommendations here. Batch size can be 16 or 32. A few different learning rates suggested here, and a number of training epochs, referring to the number of times we train on the full training set. So we're using the Atom optimizer, and I believe W stands for this weight decay fix, which was something that came out of like a recent paper where they learned some kind of enhancement to Atom. Something I'm kind of curious about is why this optimizer is defined by Hugging Face and not just part of the PyTorch library. So that's something to investigate further, I guess. Now, the other object that we're going to create here is the scheduler. So the scheduler handles the learning rate decay. When you do training of a neural network, usually you want to take larger steps initially, and then you want to take progressively smaller steps to kind of hone in on the optimum value for your weights. So the scheduler is what's going to handle that weight decay for us, or the learning rate decay, excuse me. So in order to do that, we need to tell it up front how many training epochs we're going to run for, and I'm going to do 4. And then based on that, that tells us how many total training steps there's going to be. So we can look at the number of training batches times the number of epochs that we'll be doing, and that gives you the total number of training steps that'll be taken. So this is a helper function that comes out of the Hugging Face library. This is what they used, again, in the glue script, so that's kind of where I'm taking this from. And we pass it the optimizer and a number of warm-up steps, which that's something I'd like to understand a little bit better. I'm not clear on that. And then it also needs to know the number of training steps, because we're going to decay the learning rate over all of the training steps. All right, our architecture is defined. We've initialized the weights. we have our optimizer set up, and we've got our learning rate ready to go. So now we're ready to actually go through the training loop. And if you're already familiar with PyTorch, then I think this loop will look pretty straightforward to you. If you're not, though, that's okay. I'm pretty new to PyTorch as well, so I'll actually kind of talk through the steps here and explain what's going on to the best of my knowledge. So a couple quick helper functions here. We're going to do a training pass, and then after each pass over the training set, we will do a test on our validation set, and we'll just measure kind of simple accuracy, number correct over total number. And then another helper function here just to print out elapsed time in a nice hours, minutes, seconds format so that we can see how we're doing and how long it's taking. Okay, so into the training loop. For starters here, we're going to try to set anywhere there's a random number generator, we're going to set the seed value so that we can have reproducible results here. And as we train, we're going to store the average loss after each training epoch, and then we'll plot that at the end so we can see the learning curve. See how the loss goes down over the epochs. We already defined the number of epochs earlier. We're doing 4 passes of the training set. So this is our main loop over the training set, or training epochs. And again, it starts with a pass over the training set. So we'll perform 1 full pass over the training set, and we'll measure how long each training epoch takes, so we can report that. We'll accumulate the total loss for this epoch so that we can then calculate the average loss once it's done. And we need to put the model into training mode. Now, you might look at this function and think, oh, does this train the model based on the name? That's not what it does. It actually just sets a flag telling the model that it's in training mode. And the reason that's important is that dropout and batch norm layers have different behavior based on whether you're doing training or evaluation. So BERT does have dropout, so this is important. We need to put the model into training mode. And then remember, our training set has been divided into batches, which has a batch size of 32. So we're going to iterate over the full training set, 1 batch at a time. Every 40 batches, we'll print out a progress update. We'll measure how much time has gone by for this training epoch. And we need to unpack the data that comes out in this batch variable. So we've got 3 things that make up our batch. We have the input IDs, the attention masks, and the labels. And this to function, to device, tells PyTorch to copy these variables to the GPU, because we will be doing this training on the GPU. An important step with PyTorch training is to clear out any gradients. So PyTorch doesn't do this automatically for you because apparently for recurrent neural networks, it's helpful for the model to just accumulate the gradients and not clear them out on each step. So we have to do it explicitly here. We just want to make sure we do that before each invocation of the forward pass of the model. So the forward pass is initiated by calling this model function. And because we're passing it the input IDs and the attention mask and the labels. And real quick, this token type IDs, this is the same thing as segment IDs, if you're familiar with that. So BERT can take 2 sentences, and it needs segment IDs that distinguish whether a token belongs to sentence 1 or sentence 2. But those are optional, and this is a single sentence class, so we don't need a single sentence task, so we don't need to provide those here. Because we're providing the labels in this forward pass, the model knows to return the loss rather than the actual outputs of the model. So kind of a little funny detail there that's not very explicit. Invoking model always returns a tuple, even if there's only 1 thing in it. So we need to pull the loss value out of that tuple. And we'll accumulate the total training loss. In order to do that, we call this item function. That just gets the Python value out of the tensor. So the loss is just a single value in a tensor. And then here's where the magic, I feel like, really happens. When you call loss.backward, so loss is just a tensor with a single value in it. But as I understand it, it's got kind of references back to all of the parameters that were used in computing that loss. And so when we invoke backward on loss, it's going to go and calculate the gradients for every parameter that was involved in calculating that value. So even though loss is just, like a single value in a kind of matrix, like it actually has all these hidden information to it. So that's where we actually perform the backward pass. Gradient clipping is a technique for preventing exploding gradients, so you can look that up if you're interested. And then the backward call calculates the gradients, but the optimizer actually makes the adjustments to the weights. And it does that using the update rule. So the update rule is different depending on which optimizer you're using. So Atom has its own update rule, and it decides how to update the parameters based on the gradients that were calculated, as well as the current learning rate and any other kind of parameters that the optimizer has. And then remember, the scheduler is decaying the learning rate for us. So we call step on the scheduler to tell it, we've taken another training step, so go ahead and update the learning rate, presumably like decrease it. And that's it. So we do that for all the batches in our training set. That's this for loop here. So once we've completed all of those batches, we'll divide the total loss by the number of batches that we had. That gives us our average training loss for this epoch. We'll store that so we can plot the learning curve later, report the average training loss and how long that training epoch took. Okay, so the second half of the epoch is to perform the validation test. So if you remember, we split our data set into our training data. We split it into 90% training and 10% validation. So here we're going to run the model against the validation set, and this is different than the test set, which we'll evaluate on once the training is finished. So we've completed one training epoch. We'll measure how long the validation takes. Just similar to the model.train function that we saw earlier, we need to call model.eval. Again, this tells the dropout layers in BERT that we're doing evaluation now, so they behave differently. Got a few tracking variables here. So similar logic here. We're going to iterate over the batches in our validation set. For each variable in the batch, we need to copy it to the GPU, and then we'll unpack it into those input IDs, mask, and labels. Now, this next line has exposed kind of a hole in my understanding. I confirmed that this is a good idea. Whenever you're performing validation, when you're running the model in evaluation mode, it's a good idea to call torch.nograd, because this sets the requires grad flag for all the parameters to false. So it saves on compute and memory requirements. What I don't understand is if the gradients are actually calculated during that call to loss.backward, then and we're not calling loss.backward here, then why is this line necessary? So I'll have to keep digging into that, or if you know the answer, please share it in the comments. We'll see what we can figure out. So again, we're doing validation, going to do a forward pass. This time we're not supplying the labels to this call, and so it's going to return the outputs of the model this time rather than the loss. And the outputs are the logits. So the logits are just the outputs of the final layer neurons prior to applying any kind of activation function like the softmax. So for the purpose of classification, the logits are adequate. You only need to apply that activation function if you really want to see like probabilities. So we'll get the logits out, and then in order to do some simple calculations on them, we need to copy them from the GPU back to the CPU and convert them into NumPy arrays. We'll use that little flat accuracy function just to get a quick measure of accuracy on this batch. So we've got to accumulate the total accuracy across all the batches, all the validation batches, and then we're tracking the number of batches here. So we'll do that for all of the batches in the validation set, and then we'll print out the accuracy there. So I've already run this cell, so let's take a look at the output. So we've got our 4 epochs. Looks like the training takes about a minute each epoch. That's pretty good. Let's see which GPU I have currently. GPU device 0, torch. I was given a P100. So if you're given a K80, which I often seem to get, it will run a little slower. Let's get back to the bottom of the training loop here. All right, yeah, so 4 epochs, each epoch takes about a minute. Validation takes a couple seconds. Then we can plot our learning curve here. This is just the average loss on a batch over the training epochs. And that should say epochs there, not batch. Good. Now, before we move on to evaluating our model on the test set, there's one more thing I wanted to share with you here. This is something that kind of bugged me about the PyTorch training loop here that I think maybe comes from my instincts as a software engineer. So here's what bugged me, and I've seen some comments from other people out there too that had kind of the same question. So I thought I'd share the insight. So in this loop, the optimizer is what changes the weight values, right? But we don't see any code here that explicitly takes those new weight values and gives them to the model so that the model can use the updated weight values, the next time it does a forward pass. And similarly, the scheduler updates the learning rate, but we don't see any kind of explicit communication of the new learning rate to the optimizer. So really what's going on is just that the model object and the optimizer object, they both have a reference to the same set of weights in memory. So they both have the ability to read and write those weights. And same with the learning rate. Both the optimizer and the scheduler have the ability to read and write the learning rate. And just to show you how that happens, we can kind of go back to where we created the optimizer. So when we create the optimizer, we give it the parameters from the model. And so I guess this is kind of like a pass by reference where we're not just giving it the parameter values, but we're actually giving it the reference to those tensors so that both the model and the optimizer can read and write them. And then again, when we create the scheduler, we give it the optimizer. So there's a tie there where they can share that learning rate value. Okay, little detour. Okay, so the validation set was a holdout from our training data. The Colab benchmark has an official test set. So now we're going to apply our trained model to the test set to see how we score on the Colab benchmark. And the scores for COLA use the Matthews correlation coefficient rather than simple accuracy. And the way this metric works is, +1 is the best, -1 is the worst. And the main reason we use it is that the test set is imbalanced. There are significantly more correct sentences than there are incorrect sentences. So the Matthews coefficient kind of corrects for that. Okay, so we need to perform all the same data preparation steps that we did at the beginning of this notebook. So I won't read through this. This one's a little consolidated. I put all the steps into one cell since we've already kind of discussed what's going on there. And then similarly here, we're going to do another evaluation. So very similar to the validation code that we just looked through. And We'll get our logits. Yeah, and so here, just to show you, the class is imbalanced here. So positive samples are 354 out of 516 test cases. So the 68% of the data set is positive, meaning grammatically correct. So if you were to simply predict grammatically correct all the time, then you would get 68% accuracy on this benchmark. So the correlation coefficient's used in place of that. To calculate that, it's defined in scikit-learn. So we'll calculate all of those for each batch. You can take a look at the batch just to see kind of the variation in performance across the different batches. Looks like a couple of these that did pretty poorly. The last batch only has 4 test sentences in it, so it's a smaller sample size than the rest of these. But if we combine all the predictions and calculate the coefficient for the entire test set, then we get 0.529. And there's a leaderboard here that we can check out. See if we've got BERT on here. So there's a lot of models here now that have surpassed BERT. I wonder if BERT's even on here. BERT plus single task adapters. Interesting. Oh, Jacob Devlin. There we go. So this would be the original 60.5. So he used the large size of the model. The other thing to note about this benchmark, as I understand it, because the test set is small, there's actually a lot of variability to the score that you get, depending on your random initialization. And I think I've witnessed that. The score seems to vary a lot every time I make minor tweaks. Let's see. Let's take a look at this link as well. So this is the documentation for the Hugging Face library. So they got in their example script gets 48.87. So we know we haven't done anything wrong because we've gotten similar accuracy to what the Hugging Face example code gets. All right, so I think that about covers it. I'll show you just a couple good things to know here. If you're running in a Colab Notebook, you can save your model, you can save your trained model to disk, but know that you're going to need to move that model somewhere else in order to have permanent file storage. So first of all, this is the code in the run glue script, which will save the trained model to disk. Just out of curiosity, we can run some Linux commands here to look at what files are output by that process. And we can see that the biggest file by far is the PyTorch model, even bigger than the vocabulary. So here I'm just printing out the size of the model in megabytes, 418 megabytes. And then if you want persistent storage, one nice way to provide that or to have that is to use your Google Drive. One thing that's nice about that is that the bandwidth. If you download the files to your local computer, then you're going to be using up some bandwidth to do that. Whereas if you just copy them to your Google Drive, then it's all within Google, and you don't see any of that file transfer on your own internet connection. So once you've got it mounted, you can use a Linux command to copy all those files into your Google Drive somewhere. And then here's the code for loading it back from disk. Last quick note here, there is this, in run glue, there's this weight decay functionality, but they have it set to 0 by default. So I didn't include this since the code is kind of a little confusing, but if you're interested in applying weight decay, here's the code with some comments. Thought I'd include it since I had it. All right. Thanks for sticking through the notebook, and I'm looking forward to the next episode. not sure whether it's going to be on maybe semantic similarity of sentences from BERT, or we might start to get into the architecture details. So we'll see where we go next. Thank you, guys.